Hello everyone, welcome to this week 10's lectures on the course on linear systems theory. So this week we will focus a bit on output feedback of the system. So far in our design methods of pole placement, we saw a controller designed via the standard state feedback such that the closed loop system is either stable or it has poles at some desired predefined desired locations. Usually the state may or may not be available for measurement. In that case we may, so what is available for measurement are the outputs. So in this lecture we will focus on how to design controllers, well not the design will come up a little later, but what is the analysis part of it, or what are the little concepts that we need to build on before we go to the design process when we have outputs for measurement. Okay, so this is to do with the concept called state estimation. Okay, so why do we need this state estimation? So we start as usual with the LTI system, x dot is ax plus bu. Similarly, you can also do it for the discrete time version, so nothing really changes. So the standard control problem which we saw until now was to design a state feedback controller of the form u equal to minus kx such that A minus bk is either a stability matrix or also has eigenvalues at some desired locations. So eigenvalues of A minus bk could be at some predetermined location mu1 till mu n, right. And then we saw a bunch of methods of how to construct the K matrix. This was typically called pole placement. We started of techniques using just compare the coefficients of the characteristic equation or look at the controllable canonical form, or even towards the end we had derived something called the Ackermann's formula. Okay, so that was good until you could measure the x, right. So what is crucial here is measuring this x. But in most cases only the output is available for measurement. So when the output is available for measurement, the control law u equal to minus kx cannot be directly implemented on the system, right, because I really do not have access to all of the x's of the system. However, we know something called observable systems and also detectable systems. So what we will look at in this lecture is to just to relate these two concepts and see, can I design some control law that would still stabilize my system or have my closed loop poles at mu1 till mu n. Okay. So what was about state estimation? What is about, let us begin with what was about observable or detectable. So if the pair AC is detectable or observable, it should be possible to estimate the state x from the system's output up to an error that vanishes as t goes to infinity. So this was the definition, right. So in observability I was interested in measuring x t naught from the future inputs and outputs where the interval was given from t naught to t1. So I was measuring x t naught, right. So that was my definition of observability, and similarly with the constructability. Okay, so what was happening here is, if you look at x t naught, I was only measuring the value of a state at a particular instant of time, whereas the implementation u equal to kx, one needs a continuous estimation of all the states, right. So just measuring x at t naught or the initial time does not really solve my purpose, but what I want is a continuous feedback of states u equal to kt. So this, if I write it in terms of time, this should be something like this, minus k x t, right, maybe for all t if my initial time is 0, right. Okay, so what do I do to get an estimate of this, or to get an estimate how the states look like? So we start with what is called an open loop state estimator, and to construct this state estimator I start with what I call as a copy of the original system with some new states. Let me call this x bar, right. So let's typically in what I would like to do is to feed back this u equal to x sorry, k times x bar instead of x equal to, instead of u equal to minus kx, okay, because this is not really available for measurement, but I kind of construct a copy of the system with new states x hat, or states or the copy or the system which is a copy of the original system has states x hat in such a way that now I can define the error between the what I call as the estimated state and the actual state. And what I really want is that the error should be equal to 0, that the estimated states which is being fed back is equal to the actual states that the system needs, right. So, if I just look at the error dynamics, it is easy to derive that E dot is x hat dot minus x dot, that will be simply A of x cap minus A of x. So, this will simply be A, this x hat minus x, that will be A times C, and the b's will just cancel out, right. So, I have a system which now looks like this, right. So, E dot equal to AE. Now, I want E to go to 0. So, when is this possible? When does the error go to 0? Well, it is obvious. So far what we have learned is that if A is a stability matrix, then the open loop state estimator results in an error that converges exponentially fast to 0 for every u, right. So, there is nothing really depending on u here, right. So, I start with a copy of the system, and I see that as long as my system is stable, it results in an error that converges to 0. When error converges to 0, I know that this estimate of the state converges actually to the original state, and this is what I want for feedback, right. Okay. So, problems arise when A is not a stability matrix. Okay. So, what if A is not a stability matrix? Then let us construct what we now call as a closed loop estimator, which looks like this. So, x hat dot is A x hat plus B u minus this little term here, right, minus L y cap minus y, or y hat minus y, or y is so this will also be a hat here, y hat is C x hat plus d u. Okay, the error is again of the form what was here, and that was x hat minus x. Okay, and if I just rewrite the dynamics of E dot in terms of this new x dot, and of course, x evolves as A x plus B times u. Now, what I have is the error dynamics now as a function of A, well, this is known to me, C is known to me, and some matrix L which we can design by ourselves. This is like a design parameter or a design matrix. So, if if my A matrix is not stable, I can always choose a matrix L which makes A minus LC a stability matrix, right. If A minus LC is a stability matrix, then again E will converge to 0, and therefore, x hat will converge to x. Okay. So, to summarize, if the output injection matrix gain L, so I call this the output injection matrix, right. So, this is available for design, that makes A minus LC a stability matrix, then the estimation error converges to 0 exponentially fast for every input u, and therefore, x hat converges to x. So, two things we have seen: to design an estimator, like I need an estimate of the state. When the open loop system is stable, then it is pretty straightforward, right, to design this. Whereas, when A is not stable, I need to do a little bit of modification to get an estimate, to get a copy of the system which looks like this, and the parameter L is free, is a design parameter or a design matrix such that A minus L of C should be a stability matrix. Now, obvious questions will arise: how do I choose the L matrix? Can I always choose it or not? And based on what we learnt in controllability or stabilizability, the answer should be slightly guessable, right? You can guess under what conditions A minus LC is a stability matrix when I have L as a design parameter, or I can choose, or I can construct the matrix L. So we will see what are these conditions. So analogous to controllable and stabilizable systems, we have couple of necessary and sufficient conditions for state observation. So first is when the pair AC is detectable or even observable, you can write it. If the pair AC is observable or detectable, then it is always possible to find a gain matrix L such that A minus LC is a stability matrix. Okay, so first let us try to understand this in terms of duality and then come back to our system, to the original system. So I have x dot is A times x, B times u, and say for simplicity y is Cx, and I kind of just ignore the d for the moment, nothing really changes, it's just with a loss of generality I can do this. And say I have now a dual system z dot is A transpose z plus C transpose and say some, okay, let us call this some input, and say some eta is B transpose z. Okay, so what I want is that, well, that A minus LC should be a stability matrix. So here in this case I want to choose V of the form minus K, sorry, let us call this L times Z such that A minus L, okay, let us say A minus C transpose of L is a stability matrix. Okay, this is L here, right? Or in other words, I can also place or it also yields, or it also places the poles of A transpose minus C transpose L at desired locations. Okay. Now, when is this possible? If I just look at, so this turns out to be like a standard pole placement problem for linear systems, which we saw earlier. So what was the necessary and sufficient condition for pole placement of x dot is Ax plus Bu with u equal to minus Kx? Well, that was that the A pair AB is either controllable or the weaker version stabilizable. Okay. Now, similarly look at this here. So, what I require for a pole assignment like this or even stabilization thing is that the pair A is controllable, okay, or if I, so controllability of the dual system, so this is controllability of the dual system, this is equal to observability of the original system. So, this is my original system, this is I can call my dual system. Okay. So, a necessary and sufficient condition would now turn for this observer design is A times C is observable or at least detectable. Okay. So, that is what this results will tell us. When AC is detectable or observable, it is always possible to find a gain matrix such that A minus LC is a stability matrix. So, these are both necessary and sufficient conditions. Further, Now, what we saw here is in terms of not only that A minus, not only that this matrix is a stability matrix, it can also place poles at desired locations. So, under the assumption, or if the pair AC is observable and given any set of n complex numbers lambda 1 till lambda n, there will always exist a state feedback matrix L such that A minus LC has eigenvalues at precisely these locations. It is very similar to the pole placement problem that we saw while we were doing a control design, right. The duality is a little easier to check. We could still do with the standard observability definition and go on checking that these are actually necessary and sufficient conditions, but now we have the very nice tool in terms of duality. So, we may rather exploit that tool than just going for another rigorous proof of these two conditions. Okay, so now how do I design a stabilizing controller now through what I call as output feedback. Okay, so let us start again with the LTI system. X dot is Ax plus Bu, y equal to Cx plus du, and let me assume that u equal to minus Kx is a stabilizing control law. Similar things would also exist for discrete time systems. So, whatever I am doing here can be directly translated to the discrete time systems with the appropriate definitions of stability in terms of eigenvalues within the unit circle and so on. Okay, so let me construct this this observer of this form x dot or x hat dot is Ax plus Bu minus L y hat minus y hat is C x hat plus du. So, let this be a state observer for which I can design in such a way that A minus LC is a stability matrix, which also means that I start with the assumption that AC is observable and that the pair A comma B is controllable. Okay. So, usually the state may not be available for measurement, right. So, when the state is not available for measurement, I may want to use u equal to minus k x hat, which is the estimated state, instead of the actual state. Okay. Now, once I do this, how would my system look like? Okay, so loosely speaking, what I am trying to do here is x dot is Ax plus B times u, where I would want u to be some k times x, but I do not have a k x for measurement, but all I have for measurement is some output y, and based on this can I construct an observer, right, with this x hat dot is A x hat and so on, which will give me an estimate of x hat, and this x hat can be fed back as my input. Okay, not a very good block diagram, but something okay to just visualize what is happening. I do not have x for measurement, but based on this y, I construct this x hat and then feed this back to the controller via this form. Okay, and now what do I know from previous slides is that, well, if as long as A minus LC is a stability matrix, x hat converges to x. Okay, now what can I say about, while I do these things, there is some loop that is happening, and is a closed loop system stable, right. So, let us quickly verify that. Okay, so what do I have is x dot is Ax plus Bu, and say y is Cx plus du, and a stabilizing controller of the form u equal to minus kx, and the observer or the state estimator looks something like this: A x hat plus Bu minus L y hat minus y, and output looks something like this. Okay, so if I were to say I feedback u equal to minus k x hat, and let me check what happens to the overall system here. Right? So, I have two things here, right. One is the dynamics evolving in x, which should be such that u such that the pair A minus or the matrix A minus Bk should either be stable or should have eigenvalues at some locations mu1 till mu n. Okay. And moreover, I also have this observer dynamics in such a way that this matrix A minus L times C is stable and also has eigenvalues at say some lambda 1 till lambda n, right. And now all of these dynamics together must be stable. Okay. So, x hat dot is A x hat plus Bu minus L. Okay, what is y hat? Y hat is C x hat minus plus du minus y. Okay, I can also write this equivalently as x hat dot is equal to A minus LC. Okay. Now, what is u, right? U is equal to k x hat. So, I can write this as B k x hat. So, I will have a plus so, it is be a minus, right, u equal to minus k x hat. So, I will have a minus B times k, right. And then what is y? Y is C x plus du. I plug this here and I will have another term plus L d k x hat. Okay. So, I start with the dynamics of x hat, substitute for u as minus k x hat, and I have now something like this x x hat dot is A minus L c minus B k plus L times d times k x hat plus so what will remain is this L. Okay, I can just put this like this at L times y. Okay, so in this u also I substitute u equal to minus k x hat. Okay, so and let's just let this y be as it is. Okay, so so once I do this, I now want to look at how my error dynamics looks like, right? E, which was x hat minus x, and I am also interested in how my original dynamics themselves perform, right, which is x dot is A x plus B times u. Okay. So, the total states that I am interested now are x comma E. Okay, I will just do x transpose E transpose transpose, right. So, first, okay, what do I have now about E, right. So, E dot is A minus L c E dot, that is what we derived earlier. Okay. Moreover, x dot is A Ax plus B u, this is A x plus B u is minus k x hat. So, what is x hat in terms of E? X hat is E plus x. So, I will have this A x plus B, okay, so recognize this, minus B k E plus x. So, this is x dot is A minus B k x plus A minus B k x, and I will have a minus B k E. So, the overall system in terms of the states x and E will now look something like this, right. So, the state space model for the closed loop system takes this form. Okay. Now, I just want to look at the stability of this, right. So, the closed loop system with output feedback controller results in a system whose eigenvalues are the union of eigenvalues of what do I do for the pole placement with the state feedback law, and also I am looking at the eigenvalues now of the state estimator with A minus LC. Okay, so this will be the total eigenvalues of the closed loop system, right. So, and therefore, the conclusion of stability will just be on where are my eigenvalues of A minus Bk and A minus Lc, right. So, the closed loop system is of course stable because we start with the assumption that A, B is controllable or at worst stabilizable, or NAC is observable, or at worst it is detectable, and therefore the closed loop eigenvalues which are depending on the eigenvalues or the union of eigenvalues of A minus Bk and A minus Lc will form the eigenvalues of the total system, and therefore the closed loop is actually stable, right. So, the answer here is yes. Okay. So, one interesting thing also to look at is when I introduce an observer in the system, right. So, starting with the state feedback u equal to minus kx, I just have x dot equal to A minus Bk, and I can do a bunch of things from stabilizability to pole placement and so on. Now, if I put on top of it an observer, does it really affect my original system, right? Does it also interfere in the poles of my original system of A minus Bk? So, whatever I do with the observer should not really change my original design procedure, right. So, let us see what happens in that case, right. So, what is the effect of the addition of observer on the closed loop system? Okay. So, we will just try to derive a few things here. Okay. So, I have the closed loop dynamics in the state and the error in the following way: A minus Bk, B times k 0, and A minus Lc times x times E. Now, okay, what are the poles of this system? Okay, so I just do Si minus this entire thing of A minus Bk 0, A minus Lc x, sorry, Si minus A, the determinant of this equal to 0 will give me the characteristic equation. Okay, so mind you that x is in Rn and the error is also in Rn. So, the overall system will will be of dimension R 2 times n. Okay. Okay. So, if I just solve for this, it is easy to check that I am essentially solving for this Si. So, this will be this identity will be I 2 n, right. So, the identity of 2 cross of dimension 2 times n. So, okay. So, I will have Si minus A plus Bk Si minus A plus Lc equal to 0. Okay. So, this will give me the solution to this will give me my closed loop poles. Okay. So, what are the closed loop poles? Well, the first n poles will be the poles which come as a result of pole placement. Okay. And these are the poles due to observer design. Okay. And what you see is that these two do not interfere with each other, right. So, there is nothing here. So, whatever happens with the L, the C, the pole placement component remains the same and vice versa, right. So, whenever I do a simultaneous or design an observer and a controller, the closed loop poles of the system consist of the poles due to pole placement alone and poles due to observer design alone. So, nothing really changes, right, in the design, or the poles due to pole placement remain unchanged by the poles due to observer design, and vice versa. Okay. So, therefore, we can design the controller matrix K and the observer design matrix L independently. So, one would possibly think that, oh, when I am actually I design a controller and I just bring it to you and say, hey, design an observer for me. Does that change and have any change in my design procedure? No, I can actually design both of them separately, though both need not be done simultaneously, right. So, I design a controller, I design an observer, plug them separately, right, and then everything works. So, not that L will have some effect on K or K will have some effect on L. So, nothing like that happens. Okay. So, to end with, we will just look at, okay, what is the transfer function now of the observer based controller. Let us start with d equal to 0, and I just derive, okay, let us quickly see if we can derive this. Okay. So, the way we derive the transfer function is, okay, look at this expression here together with u equal to minus k x hat, okay, or also mean that u of s is minus k x of s. From this expression I can derive x of s. What will x of s be? X of s here will be, well, you can just take the Laplace of this. I will have s x hat of s is this entire matrix. So, let me call this a star here, x hat plus L y of s, okay, and then I just plug in for u over here and then just get an expression for relating y and u, and it turns out that, okay, this is a simple exercise, okay, maybe just for simplicity assume k equal to 0, that u of s over y of s is minus k si minus a plus lc plus bk inverse times L. Okay, a little interesting thing, just as a passing comment, is that even though A minus Bk and A minus Lc are designed to be stable, this A minus Lc minus Bk need not be stable all the time. Okay, let us just say how a typical block diagram might look like. So, let us say I have some reference signal, let us say possibly 0, and okay, I have say a ys here. So, this is essentially, so this entire thing will sit here. So, bk si minus a plus lc plus bk inverse times L, okay, maybe with a minus. Okay, and then this will be u of s, and this u of s will go to my plant, which is of the form x dot is ax plus bu, and this will give me some measurement y of s and be fed back in this way. Okay. But even though, okay, so even though this need not be stable by itself, the overall closed loop system is of course stable. That is what we saw over here, right? This actually is a complete stability matrix. Okay, so okay, I will just next time maybe do a little block diagram version of each of these components of what is measured, what is computed, what is fed back, and so on when we do the actual design. So far in this lecture we saw about state estimation. We also saw how to stabilize via output feedback. Okay, in the next lecture we will do, in addition to solving design problems which involve both designing the controller and the observer at the same time, we also look at what is called as a minimum order observer. So that will come up in the next lecture. Thanks for watching.